In this video, we will look at finding maximum and minimum algorithm. The problem is to find the maximum element and the minimum element from set of n elements. This algorithm uses divide and conquer approach. And according to divide and conquer approach, when the problem is large, then divide the problem into subproblems until the subproblems are small and the solution can easily be computed. Let us take an example of these 7 elements in an array and find the maximum and the minimum element. So here we have an array with 7 elements. So we say that the problem is large if there are more than 2 elements in the subarray. And we will divide these 7 elements into 2 subarrays. Now here we will be dividing the array into subarrays until the subarrays have only 2 elements or only 1 element remaining. Once we have only 2 or 1 element in the subarray, we say that the problem is small and we can easily compute the maximum and the minimum element. So we will divide these 7 elements into 2 subarrays using the mid index. The mid index can be computed easily by considering the start index and the end index and dividing by 2. So in this case, the mid element is 21. Therefore, we will divide these 7 elements into left subarray consisting of all the elements from first element to the mid element, including the mid element. So the left subarray will have the first 4 elements in this case and the rest of the elements from mid plus 1 to the last element in the right subarray. So the right subarray has 3 elements in this case. Now the problem is still large. So we will divide the left subarray into 2 halves by computing the mid index. So at this stage, we will have the subarray with 2 elements, that is element 34 and 56, and another subarray with 2 elements, that is elements 96 and 21. Now since these 2 subarrays have only 2 elements, that means the problem is small. And we can easily compute which element is maximum and which element is minimum by comparing the 2 elements. That is, if the first element is minimum, then the second element will be maximum, or the vice versa. So in finding the maximum and minimum, when there are 2 elements in the subarray, then we say that the problem is small and the solution of finding the maximum and minimum can easily be computed. So here in this left subarray, we can easily compute element 56 to be maximum. Let us call element 56 as max and element 34 to be minimum. Let us call this element 34 as min. In the same way, here in this right subarray, we can easily say that the element 96 is maximum. Let us call element 96 as max1 and element 21 is minimum. Let us call element 21 as min1. Now, according to divide and conquer approach, we have divided the problem into smaller subproblems and solved the smaller subproblems individually. Then we need to combine the solutions of the smaller subproblems. So when we combine the solution, we will compare max from left subarray with max1 from right subarray. If max is smaller than max1, then we make max1 as max. Otherwise, max is greater. In the same way, we will compare min from left array with min1 from right subarray. If min is greater than min1, then we will make min1 as min. Otherwise, min is the smallest. So, when we are combining the solutions from the left subarray and the right subarray, max is 56 and max1 is 96. Max is smaller than max1. So, we will assign max as 96, which is the greatest among max and max1. In the same way, min is 34 and min1 is 21. Min is greater than min1. So we will assign min as 21, which is the smallest among min and min1. So we have found the max and min for this left subarray. Now let us look at the right subarray. The right subarray is still large. So we will divide the right subarray into 2 halves by computing the mid index. So at this stage, we will have subarray with 2 elements, that is element 69 and 48. Another subarray with only one element, that is element 15. Now since the left subarray has only two elements, that means the problem is small, and we can easily compute which element is maximum and which element is minimum by comparing the two elements. That is, if the first element is minimum, then the second element will be maximum or vice versa. So here in this left subarray, we can easily compute element 69 to be maximum. Let us call element 69 as max and element 48 to be minimum, and let us call element 48 as min. Then in this right subarray, we have only one element. That means the problem is small and we can easily compute maximum and minimum element. So here in this right subarray, we can easily say that the element 15 is maximum as well as it is minimum, since we have only one element in the subarray. Now again, according to divide and conquer approach, we have divided the problem into smaller subproblems and solved the smaller subproblems individually. Then we need to combine the solutions of the smaller subproblems. So when we combine the solutions, we will compare max from left subarray with max1 from right subarray. If max is smaller than max1, then we will make max1 as max, otherwise max is greatest. In the same way, we will compare min from the left subarray with min1 from the right subarray. If min is greater than min1, then we will make min1 as min, otherwise min is the smallest. So when we combine the solutions from the left subarray and the right subarray, max is 69 and max1 is 15. So max, which is 69, is greatest among max and max1. In the same way, min is 48 and min1 is 15. Min is greater than min1. So we will assign min as 15, which is smallest among min and min1. So we have found the max and min for this right subarray. Now let us combine the solutions of this left and right subarrays. So when we combine the solutions, we will compare max from the left subarray with max1 from the right subarray. In the same way, we will compare min from the left subarray and min1 from the right subarray. So when we combine the solutions from this left subarray and this right subarray, max is 96 and max1 is 69. So max, which is 96, is greatest among max and max1. So we will assign max as 96. In the same way, min is 21 and min1 is 15. Min is greater than min1. So we will assign min as 15, which is the smallest among min and min1. So we have divided the array into two subarrays until the subarrays have only two elements or only one element. Then we compared the elements and found max and min elements. Now, once the max and min elements are computed, we have combined the solutions to get the solution to the larger problem. So, using the divide and conquer approach, we found the max element, which is 96, and min element, which is 15. So this is how we can use divide and conquer approach to find maximum element and minimum element from a set of elements. Now let us look at an algorithm to find the maximum and minimum from a set of elements. Let us call this algorithm as MaxMin. This algorithm takes four parameters. The first parameter is I, that is the left index. The second parameter is j, that is the right index. The third parameter is max, which will store the maximum element, and the fourth parameter is min, which will be storing the minimum element. Now, since the MaxMin algorithm follows the divide and conquer approach, so in the first part of the algorithm, we will handle the case where the problem is small and can easily be computed. That is the case where there is only one element in the array or the subarray. If there is only one element in the array, then the problem is small, and that single element will be max as well as the min element. So we will have the if statement with the condition I equal to j. If the index I is equal to index j, that means there is only one element in the subarray, and that element will be maximum and minimum element. Therefore, within this if statement, we will assign max and min as a of I. Then we will consider the case of only two elements in the subarray, which is also a small problem and can easily be solved. So we will have the else if statement with the condition I equal to j minus 1. If I index is 1 less than the j index, that means there are two elements in an array, and we only need one comparison to find max and min element. Therefore, within this else if statement, we will have an if statement with the condition a of I less than a of j. If this is true, that means element a of j is greater than a of I. So max will be assigned a of j and min will be assigned a of I, since a of I is smaller than a of j. Otherwise, if a of I is greater than a of j, then we will have the else statement, and max will be assigned a of I and min will be assigned a of j. So the if statement with the condition I equal to j and else if statement with the condition I equal to j minus 1 are the part of the algorithm when the problem is small. Now, remember that we have not yet divided the array into subarrays. At this point, we have just handled the situation when the problem is small. So, when the problem is large, that is, when there are more than two elements in the subarray, then we will apply the divide and conquer approach. So, we will have the else block. Within the else block, according to the divide and conquer approach, if the problem is large, we have to divide the problem into smaller subproblems. So, we will divide the large array into two smaller subarrays. To do this, we will compute the mid index. That is, mid is equal to left index plus right index divided by 2. Then we will call the MaxMin algorithm recursively on the left subarray. So we will have the statement calling MaxMin algorithm, passing the first parameter as I, which is the left index. Then instead of j, we will pass mid index as the second argument, because the left subarray is from index I to index mid, and the third parameter as max and the fourth parameter as min. Then we will also call the MaxMin algorithm recursively on the right subarray. So we will have the statement calling MaxMin algorithm, passing the first parameter as mid plus 1 instead of I, which is the left index. Then the second parameter as j, which is the right index, because the right subarray is from mid plus 1 index to index j. The third parameter as max1 for the maximum element, and the fourth parameter as min1 for the minimum element. These two recursive calls will divide the array into subarrays until the subarrays become small, having only one element or having only two elements. Now, we have to combine the solutions of the subproblems to get a solution to the original problem. Therefore, we will compare the max and min computed by the first recursive call with max1 and min1 computed by the second recursive call. So, we will have the if statement with the condition max less than max1. If this is true, that means max1 is greater than max. So we will update max. To do this, max will be assigned max1. Then we will have another if statement with the condition min greater than min1. If this is true, that means min1 is smaller than min. So we will update min. To do this, min will be assigned min1. So this is the recursive MaxMin algorithm using the divide and conquer approach, where the if statement I equal to j and I equal to j minus 1 is the small problem for which we can easily compute the solution of finding the maximum and minimum element. Otherwise, the problem is large and we have the else block where we divide the array into two subarrays and recursively call the MaxMin algorithm until the problem becomes small and we can easily compute the max and min element. Now let us analyze the max-min algorithm. Since this is a recursive algorithm, and the time complexity of recursive algorithms are computed using recurrence relations, let us look at the recurrence relation for this algorithm. The time complexity of MaxMin algorithm is O of n, but instead of the time complexity, the performance analysis of MaxMin algorithm is based on the number of comparisons done to find the maximum and the minimum element. Let us assume that MaxMin algorithm takes t of n comparisons to compute, where t is the function that takes the size of the input as n. The if block where I equal to j is the solution for the small problem, and there is no comparison made in this if statement. So there are 0 comparisons for this if block. So the recurrence relation t of n can be written as t of n is 0. That is, there is no comparisons if n equal to 1. Here we have n equal to 1 because in the algorithm, if I equal to j, that means there is only one element in the subarray, and one element means n is 1. Then we have the else if block where only one comparison is made to compute the maximum and the minimum element. So the recurrence relation t of n can be written as t of n is 1. That is, there is only one comparison if n is equal to 2. Here we have n equal to 2 because in the algorithm, else if I equal to j minus 1 means there are only 2 elements in the subarray, and 2 element means n is 2. Then when the problem is large, we have the statements in the else block, where the mid statement is a primitive statement and there is no comparison performed. Then we have the recursive calls to the MaxMin algorithm for the left subarray. So each time the recursive call is made, it is on the left half of n. And since the MaxMin algorithm takes t of n, then this statement will be taking t of n by 2 to compute. Then we have recursive call to the MaxMin algorithm for the right subarray. So each time the recursive call is made, it is on the right half of n. And since MaxMin algorithm takes t of n, then this statement will be taking t of n by 2 comparisons or t of n by 2 to compute. Then we have two if statements making two comparisons for finding maximum and minimum element. So we have two comparisons here. Therefore, if the problem is large, that is, if n is greater than 2, then we have 2tn by 2 for recursive calls plus 2 comparisons for the if statements. So this is our recurrence relation for the recursive MaxMin algorithm. Now we will use the substitution method to solve the recurrence relation to compute the complexity. Using the substitution method, we have to repeatedly make substitutions for each occurrence of function t on the right hand side until all such occurrences disappear. So let us consider the first occurrence of t of n equal to 2t of n by 2 plus 2 as the first equation. Then what will be the second occurrence, t of n by 2? T of n by 2 will be, we just have to substitute n by 2 in place of n. So we will have t of n by 2 equal to 2t of n by 2 in place of n divided by 2 and then plus 2 from the original expression, which is equal to 2t n by 4 plus 2. So this becomes our second equation. In the same way, what will be the next occurrence, t of n by 4? T of n by 4 will be, we just have to substitute n by 4 in place of n. So we will have t of n by 4 is equal to 2t of n by 4 in place of n divided by 2 and then plus 2 from the original expression, which is equal to 2t n by 8 plus 2. So this becomes our third equation. Similarly, what will be the next occurrence, t of n by 8? T of n by 8 will be, we just have to substitute n by 8 in place of n. So we will have t of n by 8 equal to 2t of n by 8 in place of n divided by 2, then plus 2 from the original expression, which is equal to 2t n by 16 plus 2. So this becomes our fourth equation. Now we have t of n and we have found t of n by 2, as well as we have found t of n by 4 and t of n by 8. So we have these four equations. Now let us try to substitute them in the recurrence relation. We will start with t of n, which is equal to 2t of n by 2 plus 2. Then we can rewrite t of n as, instead of t of n by 2, we can substitute the second equation, that is 2t n by 4 plus 2. So we have 2 multiplied by 2t of n by 4 plus 2, which will be t of n equal to 4t n by 4 plus 4 and plus 2 from the above expression. Then instead of t of n by 4, we can substitute the third equation, that is t of n by 4 is equal to 2t n by 8 plus 2. So we have 4 multiplied by 2t of n by 8 plus 2, which will be t of n equal to 8t of n by 8 plus 8 and plus 4 plus 2 from the above expression. Then instead of t of n by 8, we can substitute the fourth equation, that is t of n by 8 is equal to 2t of n by 16 plus 2. So we have 8 multiplied by 2t of n by 16 plus 2, which will be t of n equal to 16t n by 16 plus 16 and plus 8 plus 4 plus 2 from the above expression. So here we have substituted t of n by 2, then we have substituted t of n by 4, then we have substituted t of n by 8. But how long should we continue? Let us say that we continue the substitutions for I times. So when I is 1, we have the first equation, which is 2t of n by 2 plus 2, and can be written as, instead of 2, we can write it as 2 power 1 t of n by 2 power 1 plus 2. Then for the second substitution, that is I is 2, we have 4t n by 4 plus 4 plus 2, which can be written as, instead of 2, we can write it as 2 power 2 t of n by, instead of 4, we can write it as 2 power 2 and plus 4 plus 2. Then for the third substitution, that is I is 3, we have 8 t of n by 8 plus 8 plus 4 plus 2, which can be written as, instead of 8, we can write it as 2 power 3 t of n by, instead of 8, we can write it as 2 power 3 and plus 8 plus 4 plus 2. Then for the fourth substitution, that is I is 4, we have 16t of n by 16 plus 16 plus 8 plus 4 plus 2, which can be written as, instead of 16, we can write it as 2 power 4 t of n by, instead of 16, we can write it as 2 power 4 and plus 16 plus 8 plus 4 plus 2. And so on for the ith substitution. We can write the equation as 2 power I t of n divided by 2 power I plus the 16 plus 8 plus 4 plus 2 can be written as 2 multiplied by 8 plus 4 plus 2 plus 1 and 1 plus 2 plus 4 plus 8, so on till ith time is 2 per I minus 1. So we can write it as 2 per I t of n by 2 per I plus 2 multiplied by 2 per I minus 1. Now, using the successive substitution, we have substituted the function t repeatedly for I times until the expression reduces to the smallest value. That is, in this case, smallest value of n equal to 2. So now we can say that n by 2 power I has eventually reached 2, for which we have the solution, that is t of n is 1 when n is 2, which is t of 2 equal to 1. So when n by 2 power I is 2, we can write it as 2 per I equal to n divided by 2. So T of n is equal to, instead of 2 per I, we can write it as n divided by 2 multiplied by T of 2 plus 2 multiplied by, instead of 2 per I, we can write it as n divided by 2 minus 1, which is T of n will be equal to n divided by 2, and we can write T of 2 as 1 since we have reduced the expression to the smallest value. That is, when n equal to 2, we have T of 2 is 1, plus 2 multiplied by n divided by 2 minus 1 will be n minus 2, which is T of n will be equal to n divided by 2 plus n minus 2, which is equal to 3n by 2 minus 2. Therefore, the recurrence relation is reduced to a polynomial T of n equal to 3n by 2 minus 2 using the substitution method. So, the number of comparisons done by the MaxMin algorithm in average and worst case is 3n by 2 minus 2. So this is how we apply the divide and conquer approach to find the maximum and minimum element using the MaxMin algorithm, which takes 3n by 2 minus 2 comparisons. Now let us compare this MaxMin algorithm, which uses divide and conquer approach, with the usual straightforward algorithm available to find the maximum and minimum element. A simple and straightforward approach is to use two variables as min and max and initialize them to the first element. Then traverse the rest of the remaining elements in the array, comparing each element with the min and max variables, and respectively find the min and max element. So to perform these operations, we have an algorithm known as straight max-min, which takes the parameter as array A containing set of elements. The second parameter is the number of elements, that is n. The third and the fourth parameter is max and min to store the results. The very first statement of the algorithm is to initialize max and min parameters with the first element of the array, that is A of 1. Then we have a for loop to traverse the remaining elements of the array. Therefore, we have a variable I in the for loop, which is initialized to the second index. Then this for loop will iterate till the last element. So we have I equal to 2 to n. Then within this for loop, we have the if statement with the condition A of I greater than max. If this is true, that means element at index I is larger than max. So we assign A of I to max, making the element A of I as the maximum element. Then we have another if statement with the condition A of I less than min. If this is true, that means the element at index I is smaller than min. So we assign A of I to min, making the element A of I as minimum element. So this is the straight and simple algorithm to find the maximum and minimum elements. Now, let us compute the time complexity of this algorithm. The first statement is a primitive statement, so it will take unit time to compute. Then we have the for loop, which will run for n times. Remember, this for loop will not run for n plus 1 times since we are starting the iterations from the second element. Then the if statement within the for loop will execute for n minus 1 times. Therefore, we can say that the time complexity of this algorithm is O of n. Now let us look at the number of comparisons made using this algorithm. We have two if statements within the for loop, and each if statement makes a single comparison. But since the if statements are within the for loop, which runs for n times, therefore the first if statement will be making n minus 1 comparisons, and the second if statement will also be making n minus 1 comparisons. So at most, this straight max-min algorithm makes 2 n minus 1 comparisons. And the worst case is when the elements are in decreasing order. Therefore, when we compare the straight MaxMin algorithm with the MaxMin algorithm using the divide and conquer approach, the time complexity of both the algorithms is same. That is, both the algorithms takes O of n as the time complexity. But when compared to the number of comparisons, the straight MaxMin algorithm takes 2n minus 1 comparisons, and the MaxMin algorithm using the divide and conquer approach takes 3n by 2 minus 2 comparisons. Therefore, better performance can be achieved by applying divide and conquer strategy using MaxMin algorithm to find the maximum element and the minimum element.